Hi, I'm Malikeh. I'm ML researcher at the Vector Institute. I work at Arcee Lab under supervision of Professor Colin Raffel. First of all, I want to say thanks to all the organizers of TMLS for, first of all, inviting me and also organizing such an amazing event. Hope you all enjoyed it so far and you learned a lot. I personally learned a lot across different talks and all these amazing things. In this workshop, we will start by understanding what the scaling laws are and then discuss how we can rethink and challenge these principles from different perspectives to train language models more efficiently and still achieve our desired expectations. So as you can see, scaling down, powering up, can efficient training beat a scaling laws? So if you have followed AI circles, you've probably heard of scaling laws. The basic idea is very simple. The more data you have, the bigger your model, the more compute you use, the better your results. But recently, some experts think we might be hitting a plateau, and it might be your question as well. Is AI scaling hitting a wall? It's kind of like working out. At first, every extra hour at the gym makes a big difference, but after a while, the progress starts to slow down. So before answering this question and going through the talk, so let's go back to late 2024. Yeah, when you go and look at the news headlines, you see scaling optimism turns to skepticism. We have this news headline from CNN stating that AI is hitting a wall just as the hype around it reaches the stratosphere. And again, we see this news headline from Reuters stating that OpenAI and others seek new path to smarter AI as current methods hit limitations. And information highlights OpenAI shifts its strategy as rate of GPT AI improvements slows. And we have Bloomberg saying that OpenAI, Google, and Anthropic are struggling to build more advanced AI. And Time questions whether AI progress has really slowed down. And the last but not the least, we see TechCrunch mentioning that current AI scaling laws are showing diminishing returns, forcing AI labs to change course. So before answering the question, I wanted to start with a poll to see what do you think. Do you think AI scaling is hitting its limits and can no longer deliver meaningful improvements? So you can raise your hand if your answer is yes. Yeah, that's a general question, just in terms of improving AI capability with just scaling. Any not sure's? So the rest, I assume, are no, right? Okay, cool. So to answer this question, let's flash back to January 2020, the birth of scaling laws in neural language models. When scaling laws in language models were actually born, and it was with the release of this paper from OpenAI, Scaling Laws for Neural Language Models. At the time, language models were a promising area of research, but the current generation of models like ChatGPT, Claude, at the time had limited capabilities. We had yet to discover the power of larger models, and the path towards creating better language models was not immediately clear. Is the shape of the model important? Does making a model larger help it to perform better? How much data is needed to train these larger models? So in this paper, authors aim to answer these questions by analyzing the impact of several factors, such as model size, model shape, dataset size, training compute, and batch size on model performance. So many of you might have seen these famous figures from this classic OpenAI paper, and that's the main statement of this paper. The loss scales as a power law with model size, data size, and the amount of compute used for training, with some trends spanning more than 7 orders of magnitude. So how they got here? To fit their power laws, authors pre-trained LLMs with sizes up to 1.5 billion parameters, so smaller models. They train it over subsets of web text 2 corpus containing something around 22 million to 23 billion tokens. And then all models are trained with just a standard next token prediction or cross-entropy law. So here you can see the relationships they found over these like smaller scale models and the training curve they achieved to find the like relationship between the compute used, data sets used, and parameter size used to predict the test loss. And based on the results, this like relationship is defined on top of a power law as a, like this loss or test loss is defined as a like exponential function of any of these like scaling factors, whether it's like compute size, data size, or parameter size. And based on the results, the performance steadily improves with more parameters, data, and compute, and these trends span 8 orders of magnitude in compute, 2 orders of magnitude in data set size, and 6 orders of magnitude in model size. There are some useful takeaways from this paper. First of all, larger language models exhibit greater sample efficiency, requiring less data to achieve comparable test loss. Dataset growth lags behind model growth, and 8 times increase in model size requires just a 5 times increase in training data to maintain performance. I want you to keep that in your mind when we go to the next slide. So at that time, they thought model size importance is higher than the importance of other scaling factors. So in July 2020, GPT-3 was released alongside this famous paper, Language Models Are Few-Shot Learners. GPT-3 was a major turning point in AI, clearly, because OpenAI could validate their results through training an actual larger-scale model on larger-scale massive data set, and they showed how powerful larger-scale pre-training can be for language models. This was the outcome of massive scale-up, like 175 billion parameters. This was over 100 times larger than the largest GPT-2 model at the time. And it was pre-trained on a 10 times larger data set than web text data used for GPT-2. Here you can see the breakdown of the data sets used for training this model. So there are a few interesting things in this paper that should be noted here. They introduced a concept called few-shot learning, or in-context learning, as a new interaction paradigm. So they're not just talking about weight updates, they're talking about better context use. And they demonstrated that larger models are better few-shot learners. Performance improves smoothly with size, and they achieve the state-of-the-art performance across many tasks without fine-tuning, only by prompting. So for people who might not be familiar, on the left side, you can see a zero-shot prompting example. So the model predicts the answer given only a natural language description of the task. No gradient updates are performed. So here the task is translation from English to French. So the user provides the prompt. The task description is asking the model to translate a word from English to French, and then it adds the target word in English and asks the model to translate it. But in the few-shot scenario, in addition to the task description, the model sees a few examples of the task, no gradient updates are performed, and in addition to task description and prompt, we see few-shot examples of pairs of French-English words so that the model will be guided on how to do the translation. Many of you might be familiar with this, but from the scaling standpoint, I would say they redefine the scaling at this time from weight to space to context. Speaking of performance, without any weight updates, without any additional data samples used, they achieve better performance by just using the context better. So that's one new perspective to scaling, I would say. And one more important thing to note is, according to VentureBeat, GPT-3 is estimated to cost more than $12 million to train. And then later we see Sam Altman stating that the cost of training GPT-4 was more than $100 million, which is not affordable for many of us in this room. And the question is, how can we predict a model's performance without breaking the bank? That's actually where these scaling laws offer a strategy. Like you can train smaller models, fit scaling laws to predict larger model performance. And why is it important? You de-risk larger scale training of these models, and when you go and talk with an investor, with a VC, you have to justify like billions of dollars investment in your project. So that's one mathematical strategy to persuade them. And in March 2022, Chinchilla changed the scaling game. They said we have to train not only on just bigger models, but on more data. And here you can see some of the results. By the time people trained models significantly larger than GPT-3, such as Megatron, Turing, NLG, MT-NLG with 530 billion parameters. The thing is, despite their size, these models were trained on data sets smaller in size, in size to like GPT-3s. And these models did not really outperform GPT-3. In contrast, models like Gopher, many of you might be familiar with like 280 parameters, trained with more data and more parameters, achieved better performance. So in this Chinchilla paper, what they did is they trained much larger models ranging from 70 million to 10 billion parameters. Like you can see the results here. And then they trained them on more than 1 trillion tokens, much more than what was used for GPT-3, like 300 billion tokens, to fit the training curves and predict the optimal model and data size needed per flops. And if you're not familiar, like flops is floating point operations, measures the total number of arithmetic operations required to train or run a model. Something interesting to note here is that when you look at the like figures in the middle and the one on the right side, you can see the optimal number of parameters and optimal number of tokens needed for flops used for training the models. And the green line is showing the like number of parameters needed for the flops used for Gopher. So Gopher was a state-of-the-art model at the time, but as I said, the main focus, because of the takeaways of that OpenAI paper, was on model size. They were not like scaling up data as much. And here we can see for the flops used for Gopher, only 67 billion like parameters were enough, while Gopher was much, much bigger, 280 billion tokens. And the minimum number of tokens to get to the optimal performance was 1.5 trillion tokens, according to the Chinchilla paper. But they only trained it on like 300 billion tokens. So based on the results, Gopher and the state-of-the-art models at the time were all undertrained. So it seemed like the scaling laws had some foundational issues there. To validate their findings, researchers trained Chinchilla, a 70 billion parameter model. It was trained on 1.4 trillion tokens, significantly more than prior models. It was, despite being 4 times smaller, Chinchilla outperforms Gopher across benchmarks. And here you can see MMLU results compared to Gopher. As you can see, Chinchilla outperforms Gopher by 7.6% on average, in addition to performing better on 51 out of 57 individual tasks. I remind you that Gopher was with like 280 billion tokens, and Chinchilla was only a 70 billion parameter model and only trained on much larger data set. So they shifted a bit how people were looking at scaling. And the main key insight here is that a balanced scaling of both model parameters and training data is crucial for optimal results. But like, given all that, the question is, again, is AI hitting a wall? Is AI scaling hitting a wall? What does it really mean? And why is it happening? So to answer this question, let's go back to the definition of scaling laws. What do scaling laws really tell us? So scaling laws are defined based on power law equation. A basic power law is expressed as y as a function of x. So y is the performance matrix, let's say like test laws, next token prediction laws, and x can be any of these scaling factors like model size, data set size, compute. A is a constant and p is an exponential, like indicating the rate of change. So, but something that you might have seen more frequently in the literature is the one on the bottom, the inverse power law. The relationship is often, that's the kind of relationship which is often observed in LLM scalings with negative exponent. But the main important thing here is that what you usually see in the literature is the figure on the right side. So, and that's the reason why you're over-expecting AI scaling. When plotted on a logarithmic scale, both power and inverse power laws yield a straight line, indicating a linear relationship between the variables. But the reality is exponential. So when we go and go somewhere on the right side of the normal scale, the things become much, much harder. Not like each linear kind of increase in any of these scaling factors would result in linear jump in the performance. So in reality, increasing the quality of an LLM becomes exponentially more difficult with the scale. So we are exactly where we have to be. Like, we're not at the wrong point, somewhere around here. And the thing is, scaling laws describe how an LLM's test loss decreases as model size, data size, or training computer increases, typically following a power law relationship, but the reality is in normal scale. Contrary to some beliefs, scaling laws do not imply exponential performance gains with logarithmic increases in compute. Instead, they exhibit exponential decay in test loss, meaning that as models grow, each additional unit of exponential, additional unit of compute yields progressively smaller improvements. And in reality, increasing the quality of an LLM becomes exponentially more difficult with the scale. And another question that we have to ask ourselves is, what defines better in LLMs? We're talking about next token prediction loss. Lower test loss doesn't necessarily mean better capabilities. And that's a question I have from you, if you want to answer to that. Many of you might come from different domains, you work on different fields, and my question is, what does better mean in your LLM use case?
Yeah, I think better in terms of relevancy, one, cost, and throughput and latency in terms of being relevant, cost-effective, and less latency.
Thank you. Any other answers? Any other expectations more than just next token prediction loss?
Maybe toxicity, precision, or recall.
Cool. Any other responses?
Less hallucination.
Yeah. Any other responses? Thank you. There's no wrong answer. The reality is that these are all different expectations that is really hard to mathematically compress them in just next token prediction loss. And we're just optimizing these models on just probabilistic test loss definitions. But the reality is that how they can be mapped to different expectations people from different fields have from our models. So when talking about model evaluation, when talking about model evaluation, there are many lenses to one model. So there are many different ways to view LLM performance. It can be from the alignment point of view, like toxicity, a lot of these things go under that umbrella. How this model is aligned to my values, and my values can also be different from values of another company, another country, another culture. So how can they be defined in just next token prediction loss? Another thing is safety. From the safety standpoint, things might be completely different. And then what we usually see on OpenLLM leaderboard or a lot of benchmarks in the papers is about knowledge and capability of the models, question answering, knowledge completion, reasoning, tool learning, and above all of that, when we talk about specialized LLMs, the expectations really differ from one domain to another domain. The expectations in healthcare domain can be completely different from finance, insurance, education, biology. So that's one thing that we have to keep in mind when talking about the scaling, like just decreasing test loss doesn't necessarily will be mapped to these like different expectations. And many of you might also have heard of data death. We see Ilya mentioning that at his, this is a quote from Ilya from News 2024 mentioning that data is the fossil fuel of AI. We've achieved peak data and there will be no more. Most LLM training data is sourced from web scraping, and majority of the data on the net is already used, unfortunately. And the finite nature of high-quality, publicly available text data may limit future LLM scalability. And researchers should and must investigate alternative data sources to sustain LLM performance improvements. Especially after that Chinchilla paper, we now know that how data scale-up is important, but we're running out of fresh data and we do not have access to it, so what should we do? Yeah, so what's next? In December 2024, DeepSeek released DeepSeek V3, which was a glimpse beyond the scaling wall. Despite some doubts, again, large-scale pre-training continues to bring noticeable improvements. It surpassed the performance of GPT-4o, which was a big achievement for open source LLMs. Even large models like Llama haven't reached that level yet. You can see here are the benchmark performance results of DeepSeek V3 versus the state-of-the-art models at the time. And here we can see, again, larger scale pre-training is helping, despite all those news headlines back in late 2024. So it is still there. And before going to the next slide, there was a very nice talk. I had a chance to join that in SF, hosted by AIX Venture by Chris Manning. And the topic of the talk is explaining DeepSeek and its implications. Yeah, if you search that, it is available on YouTube. And it was a very nice and thorough talk about the implications of release of DeepSeek and what we should learn from that specifically, and comparing the AI ecosystem of North America versus China in terms of efficiency. I really learned a lot there, and I suggest you check it out. If you want, I can share the link later after this talk with you. And yeah, so this model was mixture of expert model with 671 billion parameters. Again, large scale model. And it had like 256 experts with trained with multi-hit latent attention mechanism and a scaled version of their MOE version in DeepSeek V2. And again, it was the result of larger scale pre-training on 14.8 trillion tokens, but trained only on comparably tiny budget, about $6 million. If you remember, GPT-3 on its own took $12 million, and later GPT-4 cost $100 million. So despite the performance, we see the budget was tiny here. And then they trained the model for 2 months over 2,048 H800 GPUs. It's still a lot of these numbers, and that $6 million might not be affordable for many of us. But comparably, we see that, again, this company is changing the scaling paradigm a bit. This was the outcome of very efficient FP8 training with very careful, good data engineering. Here is the overview of their model architecture. I really suggest that you check out the technical report of DeepSeek V3 and R1 if you haven't already. There are a lot of details to learn there. So an important thing here is that still the biggest key to DeepSeek V3's impressive performance is pre-training scale. This is a massive model trained over an equally massive data set. But I want you to pay attention to some keywords in their training pipeline. Let me go from here to their, can you hear me? Okay. So this is the training pipeline of this DeepSeek V3 model, DeepSeek R1 model. And if you look at the building blocks of pipeline, I want you to pay attention to some of the keywords, lots of data, synthetic, chain of thought, reasoning, layers after layers of post-training, and distilled. So these are the keywords that I want you to pay attention to and keep them for later in this talk. So these results indicate that larger scale pre-training jobs are becoming increasingly manageable and efficient over time, and what we need is data-centric and model-centric efficiency. Here you can see the pre-training cost and GPU usage of the training this model. So while $6 million is still a significant amount, it is considerably more economical compared to other options. That's why we've heard that NVIDIA has adjusted GPU pricing, and perhaps we are approaching the next significant jump in AI scaling. So going back to the question I asked in the beginning, yes, one solution is we scale up by an order of magnitude. We have this quote from Ege Erdil from Epoch AI saying that at every order of magnitude to scale up, different innovations have to be found. Maybe we are getting close to the next jump. But there are also other alternatives to get to the performance we're looking for. One of the keywords that I asked you to pay attention to was synthetic. Can synthetic data be key to scalable data? Synthetic data is increasingly used to train language models, but its quality and diversity can vary. This is a screenshot from a paper released by Microsoft team last year called Agent Instruct. And in this paper, they are using a multi-agent framework that automates the creation of diverse and high-quality synthetic data from raw sources like text and code. Using their framework, they created a data set of 25 million prompt response pairs to fine-tune Mistral 7B model. And they call their model Orca 3. And here you can see the comparison of the base Mistral Instruct 7B model and the one trained on the data set created by Agent Instruct. And you see significant jump in performance across different benchmarks. Orca 3 showed significant improvements over the base model across various benchmarks, outperforming models like Llama, 8B Instruct, and GPT 3.5 Turbo, which were the state-of-the-art at the time. And the key to success of this model was exactly synthetic data generation. And I talked about data-centric efficiency. So there are different techniques that people use in different papers and different model training. This is a screenshot from the paper released by our lab last year, Efficient Online Data Mixing for Language Model Pre-Training. Another similar paper is Dorami. So these are all data-centric approaches. So instead of, first of all, pre-training from scratch, they're using continual pre-training. So they get their raw data, grab an already pre-trained model, and inject the knowledge by continually pre-training the model on the raw text. And they're using strategies like changing data mixture. This very simple strategy resulted in very much smoother training and also lower perplexity compared to a state-of-the-art model. So what they're doing is they're grabbing the raw text. The raw text comes from different domains, different data groups. And when you change the mixture of the data groups or data categories used for training the model over time with a kind of a reward modeling thing, you can get to boost the performance. So nothing is changed. You're just playing with the ratio of the data subsets over time to train the model, and you're making the most out of the data. And these things are actually changing the scaling laws in the back end. So the thing is, in this paper, they reached the same final perplexity as a next best method with 19% fewer training iterations, which can be huge in larger scale training. And they improved 5-shot MMLU performance by 1.9% in relative accuracy. Another data-centric approach can be just this very simple trick. This is a screenshot from the paper released by Microsoft last year, Instruction Pre-Training Language Models are Supervised Multitask Learners. So what they did is they're using raw text mixed with instructions to pre-train models, leading to smoother and faster fine-tuning and even pre-training performance boost. So what they're doing is, so in vanilla pre-training, we are grabbing a bunch of like raw corpora like this, and then we pre-train over that. But in instruction pre-training, we first grab the raw corpora, apply an instruction synthesizer model that turns these like raw text into question answering examples, reading comprehension examples, and append that to the raw text. And this very simple strategy of mixing instruction data with raw text led to a boost in performance. So here on the left side, you can see the MMLU performance during instruction tuning of models. This is the instruct pre-trained model, and this is the vanilla pre-trained model. You can see how smoothly it's getting trained. Again, nothing is changed, just the format of the data has changed. When I said DeepSeek was doing like very careful data engineering is what I'm talking about. The data users and the AI users, that's an unfortunate thing that is happening, and I want one key takeaway of this talk be the fact that how to use these data sets that are already available in the best way. So we see a lot of us when we want to start a project, we go on Hugging Face and then see, okay, what are the popular data sets which are there? We just click the download button, go to another framework for fine-tuning, and hit the training button and done. But the reality is there are a lot of redundant data samples there. There are a lot of private information there. You have to do filtering, you have to do redundancy checking for safety aspects. And I really suggest that everyone look into what's going on in each of these data sets. Don't look at the data card on Hugging Face, which is usually nothing. It has almost no information about data explainability. And other than that, check out these data-centric things. It is not all about going for a very big model and then a very big data set. Try to make the most out of the data by these data-centric approaches. Before going to the next slide, you can search for keywords like data application, filtering, synthetic data generation, or papers like FineWeb 2, FineWeb. These are all on top of these data-centric strategies. Nothing is changed from the model perspective, but they're getting to the performance they want. So yeah, that's it. And then what if we scale from one to many language models? We're not limited to one language model and one data set. This is a screenshot from the paper from Together AI, which was released last year, Mixture of Agents, Collective Intelligence of Language Models. With the rise of the small language models, SLMs, you might have heard of Pythia, Olmo, smaller Qwen models. So these are all smaller language models. People have different definitions of a small. For big tech companies, 70 billion is a small. For academia, 1 billion is sometimes big. So in the context of SLM, I would say something even up to 70 billion parameters can be counted as a small. But with the rise of the small language models, it is possible to get to collective intelligence by decomposing the tasks and routing them to different SLMs and create a chain of LLM calls to get the final answer. So instead of having a very dense 70 billion model that cannot really easy to fit into any computer device, we can distribute the knowledge across different small language models. And for example, in this Together AI example, the prompt comes in. Here's a router. The router routes the prompt to the most relevant agent. These are agents, small language models, and gets to some intermediate outputs. And these are all chained back to back. The intermediate output, again, will be routed to the next most appropriate SLM, and it will go on until it gets to the final answer. The beauty of this work is that all these SLMs are in the smaller scale. You can host them on different devices. It can also be done in a decentralized setting, and like training these SLMs is much more efficient. But together, they got a performance comparable to state-of-the-art. Like with this model, this model could outperform GPT-4 Omni on, for example, Alpaca Eval 2. So these are the approaches. And speaking of scaling, again, we are somehow scaling the number of parameters, but in a different way. We're just like adding models instead of making the dense model bigger and bigger. And another thing that I ask you to pay attention to when we were talking about DeepSeek was reasoning. And is reasoning unlocking new scaling paradigm? You might have heard of thinking, then responding. So this is a code, this is a part from the blog post shared by OpenAI when they released O1. At the time, O3 was not out. We have found that the performance of O1 consistently improves with more reinforcement learning, train time compute, and with more spend time thinking, test time compute. So important thing here is that instead of talking about pre-training, they focused on scaling post-training and inference compute, a shift from traditional scaling laws. So they are defining new scaling paradigms, not about pre-training size, but also about inference and like post-training size. And there are important like terminologies or concepts that is good to look into, like chain of thought prompting. What is that about? It improves reasoning by generating step-by-step rationales before giving an answer. Or there were like papers like React that was out last year talking about self-reflection, which enhances model reasoning by allowing the model to reflect on its own thoughts. There are different strategies. So we also do that when we're like answering to a question, like in the middle, we just pause and try to self-reflect, but we do it in a faster way. O1 sometimes goes for overthinking. Yeah, these are the things that are happening at the inference phase, and we're not talking about the like pre-training part. O1 in particular was trained with reinforcement learning to perform complex reasoning. It thinks before answering, produces long internal chain of thought to break down problems, try various solution strategies, catch and correct mistakes. So they are pouring more compute at inference for better reasoning. So this is again another perspective to scaling. Yeah, it started with that few shot learning, and now they are talking about reasoning, and we can see how and where the story is going to. So as for the closing thoughts, several factors contribute to the recent criticism of scaling laws: the natural decay in scaling laws, the high variance in expectations of LLM capabilities, and the latency of larger-scale interdisciplinary engineering efforts. However, the issues are valid, but scaling is still effective. DeepSeek was an example. Large-scale pre-training investments will continue, though improvement will become harder. Alternative areas such as agents and reasoning will grow in performance. Scaling will remain central, but the real question is what we will scale next. And maybe we need new perspectives on scaling laws. So, in the remaining time, I have an activity for you. Maybe we can invent new scaling laws together today. What if you could redesign what we scale? What would you choose and why? I intentionally removed some of the other perspectives to scaling laws so that I keep it open here, and maybe there are things that you have on top of your mind. But when you look at it, first, let's think together about the problem framing. In addition to whatever I said today, in your opinion, what's broken about today's scaling laws?
It's mostly based on chinchilla paper, and that is really, it studies a limited architecture. And I think that what I haven't seen a lot of studies that really scaling the layers can be different from widths. We have normalization issues with increasing depths, and that doesn't really that is lost. I can't see that in the literature. A really robust study of, okay, like we are, for example, in MOA, we are increasing widths. We are limited. We know that we can't increase depths more than what we have already. What is the problem there? How we can change the architecture? And changing the architecture is going to really change the scaling laws to some extent. So it's really, I mean, the way we look at it is a very limited lens, I would say, yeah.
Yeah, that was a very great point. I always have this conversation with my colleagues and like lab mates. We're like, everything we're talking about these days is about transformers, for example. But who on the planet said that that's the main and like the only way to replicate intelligence? So it's always good to look at different architecture. There were some hypes last couple of years, last year actually, about Mamba and some like sequential modelings, but still I think it's an open question of what architecture would take us there. Transformers did great after the release of the Attention is All You Need paper and all these like models that came after that, but I think we're not limited to that, and any of you can invent a new architecture and we will welcome that. So any other answers to this question about what else is broken about today's scaling laws?
Humans in the loop. We've got to get us out of there. So the more we can automate the training process, the faster we can spin that wheel.
Yeah, that's true. Yeah, that was an interesting answer. And the factor of human in the loop is never even counted in any of those formulas, but they are there, and they have been there in GPT models since the beginning.
I can add something to that, which is a great point, because basically, I think what you mean is that the more experiments we're able to do, we can scale in a way. And that means that, like, I was in one of the, NeurIPS last year. One of the talks was about the fact that, like, you may have brilliant ideas, but we choose the one that is the simplest and takes the least amount of time to experiment. And then the more experiment we do, we can, because all these have a lot of parameters, so to find the best that works well can enable us to get a better performance. So number of experiments is another factor that is not really looked into in the scaling laws. Yeah.
Great points, yeah.
I'll continue that some more. Part of that scaling is our ability to let go of control. So we're scaling our control as well. So if we allow it to automate its own training, we lose control, and we don't want to do that. So that's a scale that we're imposing upon it.
Yeah, thank you. Very great points. Any other broken points in today's scale laws?
I think one aspect is also the fact that everyone defines their own criteria for what makes a good LLM. And a lot of these ideas are more for marketing, in my opinion, to facilitate and showcase how good the system is. For example, even with DeepSeek, they claimed that it was only $6 million to make that system, but they've had billions of dollars actually to test out their theories and had OpenAI frontier a lot of the research. So at the end of the day, the decisions and the way these things are framed are more so in terms of investment in business and driving capital towards each other, rather than actually creating like a true objective perspective on what is good, like we defined earlier. And there's many different ways to approach that. Like you were saying, training different AI together, while that can create more hallucination, if they are controlled, they could provide a better answer. So we still are very early on in this area, I think.
Yeah, cool. Very interesting. I totally agree. Any other responses? Yeah, so there are a lot of broken things in today's scaling laws. So other than whether it is hitting a wall or not, the question is it correct? Is it the thing that is really representative of how things work? And as you also somehow imply, that's what the tech world is about, and that's what like AI is about. We are greedily answering some of the questions. We are greedily solving some very like toy version of these like problems, and keep things very simple. Tesla's just a very simple formula, and with that we want to present everything in the world, but neither the data set nor the formulas are fully representative of the real world we are living in. And before deploying them into very sensitive areas, it's really important to capture them. And even if that's there, people have different opinions on the performance, as we said. Like when we talk about performance, there are a lot of metrics that are very subjective here, and when we want to meet the expectation of the people, it's really hard to get to an agreement of what good performance is. So it's broken. So let's find a way to repair that maybe today. So maybe you want to answer this. So we talked about some of the like broken parts, and we talked about what things can be scaled other than data compute. We talked about, for example, reasoning, context, length, these sort of stuff as ways of scaling, or even scaling the number of the models. And other than that, adding some efficiency mechanisms into the loop that can also redefine. What other things you think can be scaled to get there and are not covered in this paradigm?
Thank you. I'm not myself knowledgeable about that, but we didn't talk about changing the way the compute itself is done. So maybe you should think about, for example, quantum computing or other ways of computing that are more efficient.
Yeah, exactly. That's one of the, I would say, maybe model efficiency techniques that I removed intentionally, and that's one thing. Like one way to get to better performance is to add some model efficiency techniques there, and many of you might have heard about PIFT, and like this quantum computing is also there, and we see like quantized models, all these like different precisions in representative, the numerical values. We used to, like last year we were working on a project for distillation, and we just turned the numbers into like the polynomial representation of them instead of just showing them in the way they are, and we got very better performance boost in terms of like the compute needed for that. So there are a lot of things in the like lower layer that we have to rethink on how to represent and how to like turn them into the machine level language to understand that. So that's one way to do that. Thank you. Other than that.
You can do domain-specific models. So, for example, healthcare. You mentioned like the quality of the data makes a big difference, right? So if the data that you have are very, very specific to healthcare data, like human bodies, health records and all that stuff. For example, the US government, the Veterans Affairs government is the single biggest, largest record repository of human x-rays, blah, 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 and all that stuff. And in my view, just studying health, cancer, treatments and all that stuff, put it on massive LLM transformers and whatnot, just to study the human body and the effects of, you know, Alzheimer's disease and all that stuff. I think fundamentally you can find breakthroughs that are, you know, basically life-changing for a generation. So I think you can do like very, very specific, pointed, focused, zeroed in. Because in some points, in my view, it's kind of like the difference between the power of a laser compared to like this full spectrum. So if you have a laser, it's all rays of light. But if you concentrate it towards a single problem, which is how do you improve human quality of life, right? I think fundamentally you could zero into something that's more beneficial.
Yeah, that was a very great point. And yeah, other than that, something that that can also relate here is that, like, so far in this presentation and in many of the use cases, we're just talking about text. So the real world is multimodal. If you go to Jan LeCun talks, he's always talking about this physical reasoning, and he's always looking at it from the vision perspective. So in the reality, we have different senses as human beings, and that's how we interact with the world. And it's really not easy to represent the healthcare world or other domains from just like text standpoint, because we cannot really easily translate all these biomarkers, all those signals, all those interaction points into one modality. So maybe we have to scale the modalities, and right now these modalities are a bit disconnected, even in the multimodal systems. Just going to the upper layer and just fuse them doesn't sometimes really look like how the actual real world works. What would you scale other than this?
I think this is something that I've noticed a lot from the programming side. A lot of these new coding agents like Cursor and Windsurf, they have a large layer before your prompt even gets into the LLM that significantly improves the quality of the response and the context of what the LLM provides you, specifically like with these MCPs and all the other tools. And I think this layer is a bit abstracted to the particular cases that they're used in and not as open or shared between systems. And if we could improve upon this to make the queries that we get into the LLM better, there could be a substantially better result from them as well. So potentially involving AI in this portion or training particular systems that would assist us to ask better questions, because I don't think humans naturally know how to do this. You know, writing fix this doesn't exactly tell the AI what to do. And so that context helps a lot.
It's something that our lab is currently focused on, might be interesting too. Like I talked about that mixture of agents model, but it was still hosted by a single company, trained by a single company. But you might have heard of decentralized training or decentralized data, and that's also another shift to this like scaling paradigm. So all these SLMs are these agents. They can be they can live on different compute on like all around the world. Now, I don't know if you've heard of the project Yloco Intellect one by the Prime, what was the company name? I'm sorry. Prime Intellect? Yeah. Company. So what they're doing is they're looking at everything in a decentralized manner. So they are scaling up the number of data donors. They are scaling up the number of GPU donors. They are scaling up the number of GPUs that can be there in heterogeneous or homogeneous manner. So in total, we might have similar number of parameters, but now a lot more people, a lot more companies, a lot more brains, a lot more data domains, data sets are there in these like decentralized settings. And this is our goal to make a more democratized kind of environment for this. And in that scale, we have a world working together to train a like 10 billion model than just one single company. So I would say that can also be a new scaling paradigm, so that we don't look at things in a centralized manner. Just one company imposing like all its like biases and expectations into one model, and the whole world use that. If the whole world is going to be the user of the model, the whole world should contribute to that, I guess. So, yeah, I think if you had time, you can also design your own scaling laws. Like you saw those like power law formulas. Do you think if that's really the thing, or you would define those mathematical formulas in a different way? What parameters would you involve in it from the data-centric, model-centric efficiency point of view, and from all these perspectives you talked about to like get a better representative, like a scaling law that actually take all of these into account, and please share them when you got there. It's out of the scope of this workshop, but I really want people to like be aware of the consequences, be aware of the points that are broken in the scaling laws, and I hope you got some key takeaways or keywords here when you start another project. You just don't hit the download button from like Hugging Face and go there. From the data part to the model part, there are a lot of things that can be optimized that are not there in many of the tools that we are using, and this would save a lot of cost for your startup, for your like lab at the like academia, and we all have to think together how to change our perspectives. The fact that you have to have billions of dollars to train a model should be gone, and we have to be the ones who redefine these scaling laws in a way that we can democratize access to AI. So thank you. Thank you. I hope you enjoyed it. So this is my LinkedIn page, and also like Twitter, Blue Sky. If you want to stay in touch, feel free to message me if you had any questions about this presentation. We can follow up and maybe write a white paper about the scaling laws. I really want to hear more about your thoughts. And also, we've recently launched a podcast, Women in AI Research Podcast. The audience is both women and men, but the guests are women researchers in AI. This podcast is dedicated to celebrating the remarkable contributions of female AI researchers from all around the world. You can scan the QR code. It's available on Spotify, Apple Podcasts, and YouTube. We release the podcast episodes every 3 weeks and talk about different areas in AI. And women researchers come there, talk about their personal journeys and also their papers. I hope you find it interesting. The Discord channel is also available, open to public. Again, all the genders. So I hope you enjoy that. And we have time for questions. If you have any questions about the presentations or general, I'll be available till the end of the time of the workshop so we can catch up. Thank you.
Thank you very much. Thank you for the great talk. It was insightful and very interesting and made us think ourselves. I had a question about synthetic data. You mentioned several methods of using synthetic data to train LLMs. Can you elaborate a little more on that?
You mean to generate the data, or you're asking about the data mixing part?
More on generating the data. Do they use, for example, an LLM to generate the synthetic data, or do they use another method? Or?
Yeah, sure. So let's go back to that slide. I think that was this slide. So this paper in particular, we replicated that at our company last year. So this paper in particular, if you check out this, they're using LLMs, like group of agents. I think they were using graph or LangChain, something like that, for doing that. So there are a lot of like agent experts working together to turn the raw text data into different formats, like question answering, reading comprehension, and so on and on. I think it was more than 10 different domains. So it takes in the raw text, and there are some instructions that you can add to the prompt, some guidelines on how to like turn it into your like target format. It takes in the raw text and like give you the response. But I can share my personal experience with this. It is very expensive. Like for us, it was even more expensive than training on raw text data. So getting to somewhere that like the synthetic data generation is like price efficient enough to use that for training models is something that we have to work more on. APIs are not accessible for everyone. You can use APIs for like Cloud Sonnet, like OpenAI APIs. Yes, you can use them. The context length is limited if you want to go with a thorough like guideline, and then turning that into a data set that actually makes change in terms of something better than what the actually like pre-trained model is really tricky. So I shared this paper here, but it was not, it didn't end up in a very successful story. It was very expensive. And we were like, okay, we can continue pre-training on raw text. Why should we turn that into instruction data? But it was helpful. So what I saw so far is that there are two approaches to synthetic data generation. One is to hire human workforce, which is again expensive and has its own biases. You share the guideline with them, and they do the annotation for you. Again, in decentralized setting, there is a company called Vana, it's based in SF, and what you're doing is that they are working in decentralized manner with different annotators from all around the world, and they create proprietary data sets for different domains, and they ask annotators to annotate, and then they sell the data to the end user in a decentralized setting. So that's one way to do that. And another way is to use LLMs, and when we use LLMs for high quality data, you usually go for powerful LLMs, and powerful LLMs are a bit pricey, so that's the thing. But the key to that is really good prompts, good guidelines, collaboration with your clients. If you're working with a client, it's really good to define those guidelines with monitoring of like, I don't know, practitioners. It can be healthcare practitioners, a lot of those things. But there is a limitation on the quality, and the limit is the teacher model or the model that is doing that. I hope I answered your question. Cool.
I guess in a slide number 37, I was wondering how do you closing the loop? Yeah, so here, so are they beside each other in a sequential or cyclic way? And then when do you decide that you get to the point or you need to get out of the loop if they are in the loop?
Again, you have limited layers. I think they had 3 or 4 layers here, but that's something that you can scale up. So the prompt comes here, and like there are few things that needs improvement even in their model, and it was also not a super like successful project on its own, but it ended up in good results when we started training. The main problem of this mixture of agent models is the router. So training a good router that can route your question to the good model is tricky sometimes. Sometimes they overfit, and it sometimes become the case that when you have some agents and one of them is better than the others, the router always route to that one, and a lot of these is like stay idle. So these are the sort of things. And one thing is how it routes. It can be routed based on difficulty level. The question comes in like medium, hard, easy, and the easy one can go to like, for example, 7 billion parameter model, and hard one can go to the 70 billion model. So you can just shift. The number of layers is something that you can extend, but like, for example, in this example, they had 3. The prompt comes in, the intermediate response is still a good response, It again goes here. It's more like revisions. I read the paper a couple of months ago, but it comes with some revisions. And then this layer at the end is the aggregator. So one LLM at the end gets all the outputs and try to aggregate and put them together to come up with a good answer. So again, each of these can be prompted with a good like system prompt so that you guide it on how to get all those answers and turn it into the answer the actual user is looking for. So it's called aggregation strategy. That's how it works. So routing, aggregation. That's how it works.
Thank you very much for the great presentation. You might have seen the paper that published last week by Apple, The Illusion of Thinking. And they challenge and say that large reasoning models are not capable of handling complex reasoning tasks. So what do you think that could break this wall, and how could the scalability, in what context, allow the large reasoning models become capable of such complex tasks? And if you have read any literature around this topic, and I'm sorry I'm putting you on the spot about this paper, but if you could share some thoughts, that would be great.
Yeah, that's a challenging question and somehow open question at the moment. Like, the thing is, yeah, we're talking about some tricks to replicate how we actually reason. But like, for example, if you go to the inner layers of reasoning, some of those reasoning models do self-reflection, for example. And for that, you just get to a point, entropy level is high, and you're like, okay, I'm uncertain. Then the model starts to, again, think and think and think. And sometimes it even results in hallucination and not really the good results. And that entropy is not really representative of how not sure the model is, for example. So, like, I cannot give you the answer because I think that can also be an open question to do that. But I think we have, first of all, lack of good data for reasoning. And another thing is, so we have to scale that up, even if that's synthetic data generation or whatever. But like, we have to have good like reasoning data sets from different perspectives. And the reality is that these models are good with whatever they have already seen. And the question is how we can challenge them with something off the like shelf and like something that they haven't seen ever. That's one thing. And another thing is, again, maybe we have to look for another architecture. That's a long-term thing. And other than that, where to self-reflect, how to decompose the task, how to plan that. Like, these are all which lag behind in terms of automation right now. So I think, yeah, so scaling the reasoning data can be one thing. I had one answer in mind, but yeah, so with chain of thought and all these tricks we got to there, but I think these are all greedy strategies. So yeah, I don't have a very great answer right now, and I hope like next research work gets us to where we have to be. But I think the models are very much limited by whatever they have memorized already in the data. So we have to automate the models to pick correct thinking points, self-reflection points, not overthinking, not hallucinating, and maybe we need more human feedback in the loop there. And other than that, oh, that was another thing is, again, a lot of this is based on text, and part of the reasoning comes from like physical point of view, and like right now I think modalities are very much disconnected, and what we call model is understanding is really not understanding. Maybe it has already seen that physical example before. But again, I don't have a great answer for that because we know the problems, but the solutions, I don't know. I hope I answered it somehow.